Hello, my name is Nathaniel Weinman and I'm a PhD student at UC Berkeley. I will be talking to you today about improving instruction of programming patterns with Faded Parsons Problems. Learning to recognize and apply programming patterns, or reusable abstractions of code, is critical to becoming a proficient computer scientist. However, many introductory computer science courses do not teach patterns, in part because teaching these concepts requires significant curriculum changes. In this paper, we report on a semester-long classroom-based study with 237 students. We explore how a novel user interface for practicing coding, called Faded Parsons Problems, can support introductory computer science students in learning to apply programming patterns, without any explicit instruction around the patterns themselves. In this study, we explored 7 programming patterns. Programming patterns offer a critical building block as students continue to solve more and more complex problems. For example, consider L2, the pattern of iterating through a list using both the index and value of elements. The L2 pattern could be applied to a problem such as this, where a student is asked to compute the polynomial at some point x given the coefficients of the polynomial as a list. The solution iterates through the list of coefficients, using the index to determine the power of x, and keeping track of a running total. In this case, the pattern is present in the use of enumerate in the for loop, and the fact that both power and coef are used within the loop. The same L2 pattern could also be applied to this problem, where students are asked to find the index of the highest valued element of a list, then return a higher order function which acts on that index. The function keeps track of the max value found so far and its index as, similar to the previous problem, it iterates through the input list once. Again, the pattern is present in the use of enumerate in the for loop, and the fact that both val and index are used within the loop. However, when programming, there are many ways to achieve the same results. For example, another valid solution to this problem is less Pythonic and a bit more confusing to read, zipping a range with the list itself. Or, a student could solve this using a while loop, missing the instructor intent of using this question to practice this pattern, or for loops at all. In this example, we begin to see why code writing questions may be too open-ended to efficiently practice patterns. To conduct this study, we built a system for the students to use. Each week, students would get a list of problems which they had to solve in order. If a student was stuck, after a certain amount of time and attempts, they were able to view a solution to the problem and move on. Students could also view a solution if they answered a question correctly. The system supports a range of problem types, in particular the 3 focused on in this study. In code writing exercises, students receive a question prompt and are given an editor to construct a valid program. It supports syntax highlighting, autocomplete, and other helpful coding features. At any point, they can check their code against test cases and receive clear error messages about the first failed test case. In code tracing exercises, students are given a program with obfuscated variable names and asked to predict the output of a program given certain input arguments. They can check the correctness at any point. Finally, the system supports Faded Parsons Problems. Similar to code writing exercises, students are given a question prompt and have access to test-based feedback. In Faded Parsons Problems, students are given partially complete lines of code in a shuffled order. To solve the problem, they must rearrange the lines of code into a correct order, and also complete each line of code. Faded Parsons Problems significantly restrict the number of valid solutions while still allowing students to construct a program. This offers a meaningfully different problem-solving process than code tracing or code writing exercises. In our study, we explored which of these interfaces were effective at teaching patterns, which provided effective practice for eventually writing code, and explored student perception of Faded Parsons Problems. More detailed results can be found in the paper. For teaching patterns, we found that both Faded Parsons Problems and code tracing exercises are more effective than code writing exercises. Both are more likely than code writing to expose students to the pattern as they solve the exercise. For preparation to eventually write code, we found that both Faded Parsons Problems and code writing exercises are more effective than code tracing. Unlike code tracing exercises, in Faded Parsons Problems, students must still actively construct parts of the final program. Finally, we found that students preferred Faded Parsons Problems over code writing exercises. Students thought that Faded Parsons Problems were easier to solve and also helped them construct elegant solutions. Faded Parsons Problems are easy to create from existing examples and incorporate into courses, can be used immediately, and work well in online settings. This work demonstrates that thoughtfully selecting exercise interfaces can provide minimally disruptive ways to improve our computer science curricula.